I'm very happy to resume after summer vacations our virtual lecture series on quantum diamond, nanodiamond, and so on. And we are very glad to host today Dr. Fernando Meneses. We met with Fernando a few months ago in Australia at Nanodiamond and Carbon Materials Conference. And I was very impressed with his talk, how he combined together AI and this quantum sensing based on diamond, and he was kind to join us today and present his work for this audience who was not present in Australia. And let me spend couple minutes to provide you some background information on Fernando. So Fernando is a research fellow in quantum sensing within the School of Physics at the University of Melbourne, where it is very cold, just +5 or -5 centigrades today. Plus?
No, +5.
Plus. So Fernando works on quantum sensing platforms integrated with artificial intelligence methods. He obtained his PhD in physics from National University of Cordoba in 2015, working on nanofabrication and characterization of magnetic materials. In 2020, Fernando joined a group of Carlos Miriles at the City College of New York, where he focused on quantum sensing using spin defects in diamond, and also on the developing of machine learning techniques for experimental applications. Currently, he continues working in similar projects and also explores these new sensing platforms, such as van der Waals materials. Fernando, the stage is yours.
Thank you very much. Thank you all for coming. Thank you, Adamas, especially for inviting me. I'll share my screen. Please let me know if you can. Can you see my screen there? It should be the cover slide. Okay, so as Olga was introducing me, I've done a lot of experimental research during my career. And in the recent years, I've been incorporating artificial intelligence skills. And I'm very happy to present this project that we've done with other institutions in Australia. It's the University of Melbourne, CQC2T, Phaser Innovation, and RMIT University. You can see the team at the bottom. And this is a project that combines diamond sensing and machine learning to solve a real-world problem. So the outline of the talk, and please feel free to interrupt me whenever you want to ask any questions. So the outline will be as follows. I will first tell you which is the context in which we are working on, the problem that we have identified, and the objective that we've set. And then I will go into the details of our methodology, the results that we got, and the conclusions. So to begin with, what we want to do is to track an object that has a magnetic signal. This is a common problem that usually it is solved by well-known techniques such as GPS when you have to track an object. However, there are some situations in which GPS techniques are not available, for example, in closed environments, including indoors, underwater, or underground. But there, we can apply magnetic sensing technology. But even if in those cases, most of the times, the objects under tracking have very complex magnetic signals as well as the environment. So it's usually necessary to develop very complex physical models or simulations to analyze the data. And many times, that's not possible because the computational cost is too high or the algorithm times are also too long. So it would be very convenient to develop an application that relies only on experimental data. So we don't have to develop any complicated physical model. So given this context, we have identified our problem as follows. In this enclosed environment, in which we need to use magnetic sensing because our techniques are not very helpful, we need to track in real time a magnetic object. And to our knowledge, there is no method that relies exclusively on experimental data to tackle a complex situation. So our approach, our objective, will be to develop a machine learning algorithm that can be trained on experimental data exclusively, no need for physical models nor simulations, and it will be able to track in real time a magnetic object in an enclosed environment. So that objective is very broad. It can be adapted to many situations, but for this research, we have chosen the elevator system in our School of Physics building. This is our magnetic target. So it is an indoor environment, and the object has a magnetic signal. So let me introduce it, the whole system. Our real target is the elevator car. It has magnetic signals, but it's not the only element that is contributing to the overall signal. We also have to consider the counterweight that is traveling opposite to the lift. It also has a magnetic signal, as well as the steel cables and the electrical motor on top of the building. And to make it a real-world problem, we have a strong environmental noise coming from nearby electrical trams, from very frequently urban lines. Our lab is situated 50 meters away from these many lines, so we all the time measure a strong noise coming from it. So all in all, we have a complex system within a noisy environment. So we don't have magnetic information about each of the elements. Then building a physical model or accurate simulations would be very challenging, and in fact, it would require much more knowledge about the system. So what we want to do is just to take experimental data and develop a machine learning algorithm with minimal inputs about the system. So we do need to know some things, but they are very easy to measure, and they are related to the elevators, the nature of their movement. So we know that the elevator is constrained to move between level 1 and level 8, that each level is spaced 4 meters apart, and that the average speed of the lift, we have measured that, is 1.4 meters per second. So the time to take to go from one level to the next one is, in average, 3 seconds. And that sets our time scale in our problem. So with all this information, we define our goal for this particular scenario, which is using machine learning algorithm. We want to predict in real time the position of the lift, and considering our 3 seconds time scale to go from one level to the other, we've set a time resolution of 0.1 seconds. And what we want to achieve is an accuracy of 80% within 1 meter tolerance. And here I'm introducing two metrics, accuracy and tolerance. So let me explain you better what they mean. Here there is a scheme in which our elevator is traveling from level 2 to level 3 as a function of time. And I was talking before about the tolerance of 1 meter or less. But you may think that the lift is in fact a bulky object. It's 2 meters high. But what we are really targeting, or we are really thinking the lifts as a point, because the lift will only open the doors when it's aligned with one of the levels. So we can think that we are really tracking only one single point of the lift, the bottom, the floor. So only when it is aligned, it will open the doors. So that 1 meter tolerance is related to that single point that we are tracking. That's our spatial resolution for this problem. And here to talk about accuracy, I will introduce two definitions related to the machine learning approach. The machine learning will predict points one by one. So each prediction will be considered successful only if the distance between the prediction and the ground truth, I mean, that's the real position of the lift, if that is smaller than the tolerance. On the other hand, we will have to train or evaluate the model in a training dataset. So the accuracy of the model will be defined as the number of correct predictions divided by the total number of predictions. So when I say that we want an accuracy of 80%, what I really mean is that with our 0.1 second resolution, every second we will measure 10 points. So 8 out of these 10 points will be correct, will be within 1 meter tolerance. So even if some points, the 20% points, are a bit off of the trajectory, we will be able to reconstruct what is happening. And that's why we have chosen this 80% accuracy. So with all these sets, we've asked the AI what it expects from this research about combining a quantum diamond sensor and tracking a magnetic object. And this is the answer that we got from the AI, which is pretty good, but not very realistic. So in what follows, I will explain you what we did in this project, and I will begin with the setup. We have the elevator system, and 10 meters away, in the lowest level, our laboratory is located, in which we have our quantum diamond magnetometer. You can see it there as it looks like, but I will show you also a scheme in which you can see on the right image that there is a green line that represents the laser. The laser is hitting the diamond, which is sitting in a PCB with an embedded microwave circuit. The diamond has a photoluminescence response that is collected with these parabolic concentrators. Then it is filtered by a long-pass filter, and finally detected by a photodiode. And in addition, we have two samarium cobalt ring magnets that provide a constant magnetic field that will be necessary to split the quantum levels in the system. I will talk about this later. So as the main features of our magnetometer, it measures the full vector magnetic field, in this case, Vx, Vy, Vz, measured in our Cartesian laboratory frame. The sensitivity lies within 350 to 500 picotesla per square root hertz, which is very good compared to the floor noise, which is between 100 and 200 nanotesla. And the magnetic variations that we get when the lift is changing floors is always smaller than 1 microtesla. In some levels, the variation is in the order of the floor noise. In some others, it is a bit more clear what is happening. So a few more details about our sensing platform, and especially for those who are not very familiar with diamond sensing. Our sensing unit in this application is a nitrogen vacancy defect located in the diamond lattice, which, I mean, we have this very pretty diamond on the right. This is not what we have. What we have is this 3 by 3 by half a millimeter chip, which is a CVD single crystal with an NB concentration of 4.5 parts per million, which means that we have a very dense ensembles of nitrogen vacancy defects. These defects are quantum units that have energy levels, and under the effect of an external magnetic field, these quantum levels will split. So we will be able to measure that in what we typically measure, which is a optically detected magnetic resonance. So here is an example of our measurements. in this measurement, what we do is we excite the quantum defects with our microwave, and we sweep different frequencies. And because there is a magnetic field, at some point, we will hit an energy transition, and we will see a contrast in the photoluminescence. So because we have a single crystal with a dense ensemble of MB centers, we will have 4 possible orientations for the defects, and we will measure all of them at the same time. So each NV axis will split its quantum levels accordingly to the external magnetic field. The stronger the projected magnetic field along that axis, the larger the split in between fields. So in this example, we have the magnetic field mostly aligned with the MB4 axis. So you can see that these peaks are the outer ones. And the most inner peaks belong to MB1, which is almost perpendicular to the magnetic fields. So when we measure this optically detected magnetic resonance, we are able to identify all energy transitions and to determine which is the magnetic projection on each MB axis. So with that, we can reconstruct the full magnetic vector. So this is the concept. Now I will show you the measurements that we are getting. And I will remind you that our magnetometer is sensing the whole system. That means it's sensing the elevator car, as well as the other magnetic elements, as well as the noise. And on the other hand, we are recording independently the position of the lift using a camera. This camera points at the display, and the display tells us if the lift is parked at any level or if it is traveling. So this is a typical trajectory measurement of the lift. And what we really know with our camera is the parking intervals of the lift. We know that at some point it's parked at level 1, then at level 2. And then what we do to make a very simple model is just interpolate these 2 intervals, assuming that the lift has a constant velocity. Of course, there are better models to model that, but what we want to do in these applications is keep it as simple as possible, so you have to provide a minimal inputs. So with this rough approximation, we know, I mean, for sure, where the lift is parked, and we have a very good idea of the trajectory of the lift in between. So at the same time, while the lift is moving, we are recording the magnetic fields, and these are typical magnetic measurements recorded by our diamonds. So you can see, and this is the projections in the laboratory frame, the Bx, By, and Bz components. And you will notice that the Bx components is much cleaner than the other 2. And also, it shows a very clear correlation with the position of the lift. So why is Bx special? Remember that I told you that there is a strong environmental noise provided by electrical trams, and this noise is strongly directional. So it is affecting mainly the Y and Z axis, and it is leaving the X axis almost clean from noise. So in this case, we are in a frame in which one of the components is very, very clean, but if we were to rotate our sensor to any other orientation, we could measure a very different thing. For example, in this is what I call a rotated frame. Now the sensor is tilted, and we measured magnetic components, which are all affected by the noise. So now there is some correlation between the magnetic signal and the position of the lift. You can still see it, but the details are not clear any longer. So the important message here is that the magnetic information is not changing from frame to frame. The whole information is encoded in the magnetic vector. But because we represent it in different projections, we may think that there is a preferential frame. And this is the very human approach, because I mean we are guided because what we've seen. So in our machine learning approach, we will ask one more requirement to our goal, and it is that the algorithm should be able to process the data in any rotational frame. We don't need to look for the ideal rotational frame. Maybe we don't know it, and maybe we don't want to waste time for that. So going to the machine learning, this is what we will ask it to do. It has to be trained on experimental data, no physical model, no simulations, and it has to be supervised learning, which means that during training, we have to supply the algorithm with both the magnetic predictors, that's what we measure with the diamonds, and the ground truth, which is the true position of the lift measured by the camera. Then the algorithm will take the magnetic information and it will output the position of the lift. So before I go on, I would like to make a comment about this supervised learning, because you may think, if we have access to the ground truth, why are we doing this artificial intelligence approach? And the key is that we are working in a controlled environment. And by that, I mean that complex signals are complex. There is a strong noise, but the possibilities for the movement in the lift and what is happening are limited. So that means that in our case, the elevator is constrained to move between level 1 and level 8. It can take many paths. The noise is strong, but it is more or less a constant in our system. So machine learning is very good at studying a data set and then interpolating the data. So in this case, we can cover with a short training time all the possibilities for the lift, and then predict for any future time what is happening. So we don't need to rely in a camera any longer, or in other words, we have an independent source of measurements. On the other hand, if you have only limited access to your camera or to your alternative measurement platform, then this machine learning approach becomes even more useful. And thinking in these kinds of applications in which we have to have a relatively isolated environment with limited possibilities, we can have some perspectives in adapting this application for example, to an underground scenario, for example, a mine, in which we may want to track the activity of vehicles that they have a magnetic signal, or imagine that for safety reason, you want to track the position of the workers. So you could provide them with magnetic beacons, so they have a magnetic signal and you can also track them. So in this case, the problem is much more complex than our elevator. So it will take much longer to train the AI. But once it is trained, it is ready to go for any time longer. So I wanted to share these perspectives because we are analyzing a simple problem with the lift, but the concept of the machine learning training of experimental data is very strong. So with that, I will explain you how it works, the supervised learning. What we need for training the AI is a training dataset, which comprises both the predictors that we measure with our magnetometer, that's Bx, By, Bz in any rotational frame. And then we need the targets, which is the ground truth, the position of the lift measured by the camera. So all this dataset will be fed to the machine learning model. And the machine learning model, you can think it as a white box, as a black box. And in fact, what it has inside is an architecture. And this is the internal structure that it needs a human input to be designed. All subsequent learning is made automatically, but we have to choose which is the architecture of the model. So let me show you some details of our model. It is a deep learning architecture, which combines First, a block of convolutional layers, one-dimensional convolutional layers that are able to process the features that it gets from the data. We have non-linear activation functions that enhances the power of the machine learning. And then finally, a block of fully connected layers that finally can predict one by one the position of the lift. So you don't need to remember any of these details. You can, in fact, think this machine learning algorithm as a black box, that it takes the magnetic predictors and outputs the prediction of the lift. And during training, this is the image that I'm showing you is a single cycle for the model or an epoch. So at the beginning, the predictions won't be very good, but what the model will do every epoch is compare the predictions with the ground truth. And because it tries to minimize the difference between them, it will adjust its internal parameters. So the next epoch, it produces better predictions. So we train the model for a certain number of times or until some threshold is reached. And then that it's done, the model is trained, and from now on, the model will just take magnetic predictors, no reference positions, and it will output the prediction for the lift trajectory. So regarding the data sets, I'll tell you briefly that we measured along 12 hours for this research. We split this data, which is both magnetic signals and camera positions. We split it in two sets, the training and evaluation, both with 6 hours. And because we want a robust model that can work in any rotational frame, what we can do before training is take all our data, the magnetic data, and we can rotate it to any rotational frame. So we will evaluate a model in many instances with different rotational frames, compute all the accuracy results, and we will define the scoring of the model as the worst results, the lowest accuracy. So we guarantee that the model can work in any rotational frame, at least with that performance. So as I said before, the training process is automatic, but we have to choose carefully the architecture. So in order to do that, we organize our research in a series of optimization stages in which we will determine each of the architecture parameters. So some of these optimization stages are too technical, so I will only highlight 2 of them here, which have more physical meaning. One is related to the input information, which magnetic information we need for this model, and then the dataset length. For how long do we need to train this model to have a good accuracy? So regarding the input information, what we really want to answer is, do we need the full vector information, or can we just supply in this application, for example, the scalar intensity of the magnetic field or a single projection, or maybe a combination of 2? So what we really measure is Bx, By, Bz. From that, we can reconstruct the scalar B field. And in this plot on the right, I will show you the accuracy of the model for each one of the input options. And there is a line, a red line there, setting our minimum accuracy that we want. So for each option, we will train several models with different architectures and different rotational frames. I will show you an example with Bx. We train several models and we compute all results. So the whole range of results is contained in this shaded bar, this blue bar. And the diamond at the bottom, that is the worst results, which is the official scoring of the model. And in this case, if we take a closer look at this poor result, it happens when we evaluated the model in a rotational frame which wasn't aligned with the clean axis. On the other side, the best result happens when Bx is in the laboratory frame, which is aligned with this axis that is free from the environmental noise. But because we only care about the minimum accuracy that we get. We will simplify this plot, and we will only show this bar with all the results and the diamonds. And this is all the results that we are getting. If we start at the leftmost, you can see that the scalar field is very consistent, and this is expected because a scalar field is invariant against rotations. So the variability in the results is due to the different architectures that we are using. So performance there is very bad, it's 50%. So it won't be useful for this application at least. So then we have the single magnetic components, Bx, By, Bz. All of them have poor results. And in fact, By and Bz could achieve as good results as Bx in the best case. The reason that we don't see very good results for these components is that we chose several rotational frames in which none of them is very well aligned with the By and Bz axis. But if you were to take the Bx rotational frame in which the axis is free and rotate it 90 degrees, you would see the same results in By and Bz. So then if we add one more component, for example, Bx and By, results improve, but are still not good. And only in the full vector case, we are having very good results, above 80%, and very consistent. And this is, again, expected because the information is always the same. It is only rotated into a different frame. So once we have this set, we will use vector information. So this is very important because it tells us about the magnetic platform that we need. So, okay, we are using a full vector magnetometer. We go through many other optimization stages, and then we have our best model that performs well. When you train it with the whole data set, that's 6 hours of trainings, it has a 90% accuracy. So what happens if we need to train it for a shorter time because you don't have access to the ground truth for much time? This is what we do here. And the accuracy of the model is decreased with the shortening of the training data set, which is also expected. But the good news is that if you want only to achieve your 80% accuracy, you are able to train the model with less than 1 hour and still get good results. So after we've trained the model, the training is finished. We keep the model. We won't modify it anymore. It has the architecture parameters fixed. It learned its internal parameters. So now we are going to use it to predict new unseen magnetic data. So this is a 2 hours recording, Bx, By, Bz. And this is the data that the machine learning model hasn't seen yet. So we will input this, and we will get some predictions. And let me zoom in the predictions, because we are going to compare them with the ground truth. You can see that some faint horizontal lines. These are the parking levels of the lift. So one note is that the machine learning is predicting positions within level 1 and level 8. Nothing is outside this range. And this is, because machine learning is very good at interpolating that data. So it's doing a good job there. And on the other hand, it's predicting that the lift is moving between levels. So it's not predicting nothing crazy. So if you compare with the ground truth, this is what we get. The agreement is very good, about 90%, with that 1 meter tolerance. And of course, the model has some weaknesses, but all in all, you are able to reconstruct the trajectory of the lift. So for example, I will show you this point there in which the lift is in fact stable, but the ML is predicting some fluctuations. That's probably because there was a lot of noise at that moment or some event. Or in this case, the elevator moved 1 level up and then 2 levels down, but the machine learning predictions missed when we went up and then down, and it only registered that it went down. So besides these little flaws of the model, we are very happy with the results. And we think that if we need to improve it even better, there are some approaches. For example, we could implement physical informed neural networks in which we set some rules for the movement of the predictions. For example, we can say, you can't jump abruptly when you move in the lift. So these fluctuations in the left example should be avoided. However, this is a more complex approach, and you need to put a new input in the network. You have to know something about your model, and you have to code something else. And we emphasize that what we want to do is an approach that is as simple as possible, so you can deploy it in other systems, just tweaking little things. So let's look at the overall results again. We have this performance chart, and I will bring back these two definitions. A prediction is considered successful, a single point, if the distance with the real position is less than the tolerance, and the accuracy, when you evaluate the model in the testing data set, is the number of correct predictions divided by the total number of predictions. So in here, I will show you that the same model was evaluated in many rotational frames, so we get the lowest accuracy. And then we put different tolerances to see the accuracy. So this is the curve that we see. At a 1 meter tolerance, we have the 89% accuracy. It is a bit smaller than the 90% that I showed you before. And this is because we have trained the model here. We have evaluated in 50 rotational frames. So we are sure we don't have a blind spot there, and the model is very robust. So we can take a look at two other metrics in this graph. If we go to the most right, in which there is a tolerance of 2 meters, that's the highest tolerance that we can put to certainly recognize that the lift is closer to one level or another, because each level is spaced 4 meters apart. In that case, we get 95% accuracy. On the other hand, if we just want to keep 80% accuracy, we can ask for the tolerance as low as 25 centimeters. And with these results, I would like to come back to the initial goal, which was using this machine learning algorithm to predict in real time. And in this case, we have a 0.1 time resolution, which is pretty fast for our time scale. And we want to achieve an accuracy of at least 80% within 1 meter tolerance. So we exceeded these results. We achieved 80% accuracy with 25 centimeters tolerance, or if we want to keep the 1 meter tolerance, we can have a 90% accuracy. So we are really happy with the results. We believe that this method has a great potential to be applied in many other similar scenarios. We are preparing the final details for submission, and you will see it soon posted in the archive. So with that, I would like to finish, and thank you all for listening. And I would be pleased to hear any thoughts or comments that you may have. Thank you.
Fernando, thank you so much. It's very interesting. It's like some detective story or something that just one single story for the entire presentation. It's rare that happens. And maybe the most interesting thing was that it sounds, oh, you just take a commercial quantum diamond microscope and you don't say dwell on how it works or something, or just you just start to apply it to a real world problem, which is great, and combine with AI. So it was very nice. We are open to questions, so please just unmute yourself and ask your question, or you can type it in chat. Maybe I can start with my question. So one is, if you take now this technology and go to another building with another lift, can you apply it to measure lift positions? How similar conditions should be in another location in order to use this say, microscope and this trained AI system.
That's a great thing. There is this concept of transfer learning in which you can apply one AI model to another situation. But in this case, for example, it could vary greatly because we have this strong tram's noise and our floors are spaced 4 meters apart. So if you go to a very different situation in which the lift travels faster, or you have a very different kind of noise, or you have many lifts operating at the same time, you will have to retrain your model. But if you have a very similar situation, for example, let's say the lift is traveling at this more or less the same speed, the distance between floors is more or less the same, you have some noise. What you can keep is the architecture of the model, so you don't have to go through the optimization stages probably, because we really found a good configuration. But I think you will need to measure, at least for a short time, that's probably 1 hour, as I was showing before, the real position of the elevator, and you have to train the model again. But training is fun, but you have to take the measurements first.
And since you have all these recommendations already on hand for how long, what possible accuracies, and it all perfect to implement. So. And then another question is related to your diamond plate, of course. Yeah, we are all material scientists. You cannot avoid this question. So you used 4.5 ppm NV centers concentration crystal. It seems that it's quite a high density, and also at such high NV concentration, probably this T2 time is not that great. Maybe other words, is it ideal diamond crystal for your application? And what specific NV characteristic is important in this application? Say longest T2 or T2 star or something else. Some ODMR, say, parameters, say, widths of ODMR.
Yes.
Peak.
In this case, well, we are very concerned about the line width of each peak, and we are using a lock-in system. So we are filtering a lot of the noise for each peak. In fact, let me show you. Probably I have, I don't have it here. But when you have our real audio measurements, we can distinguish the nitrogen splitting. So our resolution in frequency is very good. So what I would say to this is, in this case, what we really need is a single crystal, or maybe, I mean, if we were to measure, I mean, a single magnetic projection, and we have many magnetometers, we could reconstruct the full vector. That's the main concern for our application, having the full vector. And regarding the specifications of the diamonds, I think it can vary. I don't remember right now which is the T2 or T2 star methods values. You can use a lower concentration, I'm sure. Probably you will have to average a bit longer. For example, we are measuring at 10 hertz. I mean, this is how much, I mean, in every 0.1 seconds, we get the average measurements, and this is what we get for the ODMR. So probably if you have a poorer ODMR spectrum, you could average for, let's say, 0.5 seconds. So you won't predict at 10 hertz, but at 2 hertz, but still compared with your target time scale, that will be still good.
And Fernando, would you predict that you would improve resolution if you did the opposite? So maybe if you took more time to average, maybe you'd have less temporal resolution. Could you get better, I guess, if your elevator model would be spatial resolution of the elevator, but let's say less noise in your measurement? Do they relate in that manner?
Yes, I think so.
Huh.
I think that there is at some point, this is not the same application, but I think there is a limit for the model. For example, there is some situation in which when the leaf is at level 4, which is almost in the middle, the counterweight is very close. So probably our predictions are a little worse because the magnetic fields are more blurry. So definitely improving the signal to noise ratio will improve the predictions. At some point, I think there will be a limit. For example, we can reach 90%, 95% accuracy, because maybe, I mean, there are some situations that are naturally complicated to analyze. But I mean, yeah, if you could have the perfect measurement, probably, yes, we could reach 100% accuracy.
I guess I just wanted to have one quick question just to clarify something. When you were talking about the different rotational frames, and you're basically, how are you're actually rotating the plate in that case, or like how does that, because it's a large ensemble, like it's all connected to the optics, and so I'm wondering about how that actually physically happens.
Yeah, in this case, we are not rotating the sensor because it's
Yeah.
the sensor is set in this case. However, the team in charge of building the sensor, they are developing a portable version, so it could be rotated in the future. But what we do now is make a rotational operation. We just take our data, multiply it by a rotation matrix.
Okay, that makes sense. Yeah, so it's a mathematical transform. It's not that you're sampling with the instrument in a different configuration.
Yeah, for this application, yes, we are just simulating how we rotate the sensor. Yes.
Okay, cool. Great, thanks. Yeah, and that was also an awesome talk.
Yeah, please just unmute yourself.
May I ask you a question? I missed a little bit beginning of the talk, but what is actually input, like roughly dimensionality of the network, and what is the output? As I understand, you have this 3 vectors, yeah?
Yes.
Over time, 3 array of 3 by large amount of points. So what is actually input in your network and what is output? That was a little bit confusing. And what is the accuracy? You measure basically accuracy for every floor. Yeah, that's as I understand. What is accuracy exactly?
Yes, thank you very much. That's a great question. I skipped some details about the machine learning inputs and outputs because they were maybe too technical. So let me explain you here. I didn't show this is how it really works. We have our magnetic predictors on the left image. That's Bx, By, Bz. We measure at hertz, so we have a lot of points. And on the other hand, we have our target measurement, our position. So what we do in order to improve the machine learning performance is at any time t, we feed the AI with the most recent history of what was happening, and we feed it with 4 seconds of the previous history. So the input for the machine learning is a matrix which has 3 channels, Bx, By, Bz, and in each channel it has 40 points.
Okay, so you split it by many segments which each fed to the neural network, and you get the output which is 1 point or what?
Yes, for every time window. I mean, the time window is long, but you are always at the latest time. You are at the current time t. So that and processing is very fast. So you feed it with the last 4 seconds. And then for each time window, you get a single output prediction. So as time goes by, you get different predictions. For each time window, a single prediction, and you then reconstruct the trajectory of the lift.
And one related question, because you used 1D convolutions, as I understood from your presentation. Because if history matters, if you talk about position, probably speed, acceleration, whatever matters, because future history probably wouldn't matter much. What matters is the past history. Yes. Did you consider like recurrent neural networks instead of convolutions? Maybe they would work better in this case.
Yes, we've done some research, and I think that, well, recurrent neural networks are more focused in predictions for the future. And what we really want is know that what happened now. So this is why we used a convolutional neural network. It's like looking at an image, but rather than colors, you have magnetic components. And we've tried a few more architectures, and one-dimensional convolution layers are the ones that work best. And other thing that we tried is to change this. This is a plot of how the accuracy varies as a function of the time window's length. So if you use a single time window, for example, a single point, you just submit Bx, By, Bz at the point of your measurement, you get still good results, but the longer the time window, the better the results. So, I mean, we confirm that machine learning works better if you supply some history, probably because it denoises or it gets the velocity acceleration. We don't know what it does, but it works better.
No, yeah. Okay, thank you.
Thank you very much.
If somebody else have a question, it's a chance to ask. Okay, probably at this point, Fernando, thank you so much for your lecture. It was a great start of your day today to give this excellent lecture, and so people learned a lot from you and all these tiny details, how you proceed solving your task is very, very instructive to consider some other problems in the world where this magnetometry based on NV centers can be useful. So congratulations with this very nice work. We are looking forward to your publication, and thanks again for your great lecture.
Thank you very much. I'm very pleased by being here and also to share the work. And I thank you very much for all the questions. They are very interesting. And we believe that, yes, we can apply NV magnetometry, I mean, with a great potential to magnetic sensing, and also combine it with AI to get very good results.
Okay, great. Thank you. Bye.